great. Thank you so much, Lorenzo, for the introduction. We have spent a lot of good time in Italy back then, building up actually the SOTA robot at that time, the iCup. We were involved in a lot of interesting research, and you have seen all the big hypes about humanoid. Actually, a lot of things have been done like more than 10 years ago already, and now it's alive again. So it's great to be here, to be invited. I just flew from Silicon Valley, just arrived like this morning in Heathrow, and I travel right here. So I'm kind of half sleeping, like I'm doing my sleep walk and sleep talk. So forgive me if I blah blah too much. I joined the UCA actually before the robotics and AI program started. So at that time they don't have the title like professor in robotics and AI. They only have Swan Robotics, and they hired me. And I said, can I change it to because I'm not doing Swan. They said, sorry, it's system automatic. You cannot change it anymore. But anyway, the actual research I'm doing is robotics and AI, or AI-powered robotics. So I've met some kind of AI genius from your batch during year one. I'm not sure they are here today, but the second time I see you guys now is that you guys are already year three. So in the middle, I was away in the industry, doing a lot of other projects, which you will see later. Okay, so I will briefly give a little bit introduction about what actually has been done like more than 10 years ago, a little bit like old man talking. I just show you that what was done during the previous wave of robotics. And then I particularly will look at dexterity, despite I'm coming from the locomotion background, but locomotion is mostly solve the problem. As you can see, the robots are dancing, doing backflipping much better than I do, right? I can't do backflipping. So now the attention shifts more towards learning and manipulation-based stuff. So I will cover several different strands. And in the end, I will still touch a little bit locomotion because this is the research going on down there on the ground floor. And in the future, I will give a little bit outlook. And I'll also introduce a new project which we will collaborate with the UK company during the IXN. You will have IXN project very soon. So I will give a little bit introduction about that. So this is a slide I've shown like in 2023. So this is what I was putting there. I wanted to just bring it here again today, like 3 years later. So at that time we were thinking like we're doing a lot of research here, and this is very, very hard to do the task reasoning. And at that time, the ChatGPT is just out. We can use large language model to do a little bit task reasoning. Not perfect, but it's kind of working already. Can break down different tasks and has common sense. As we tested in 2023 February in ETH with a lot of researchers, it can break down, grabbing the mark from the table, put a harness somewhere. I can break down into 8 steps. It makes 1 step wrong. Then we tell it, and then it can correct into 12 steps. So at that time, it's already there, kind of there, but not perfect. But nowadays, it's getting even much better without making such mistakes. So what has happened in the past 2 more years is that large language model, VLM, then VLA, and water models even, is getting more and more powerful, and it can do a lot of task reasoning separately. It's called embodied train of thoughts, or simply kind of physical AI reasoning. And with the VLA paradigm or water model-driven kind of the VLA type of control, it can do all these 2 things together, end-to-end, without breaking down into different kind of modular sense. Of course, this is still up to discussion how human brain is doing it, because we do it very differently. We have visual cortex here, and then I think it's kind of prefrontal lobe or something, or frontal lobe somewhere there, and then the motor cortex, then the prefrontal cortex. So we have different parts. But the machines are different. There's always a way that machine can brute force learn everything fusing 2 different brain parts together. It's quite interesting. So I would like to bring up this grand picture. So it's very, very interesting. I'm putting it this way, that this is all what has happened before. Like this is the research what we have been doing before the VLA paradigm started to kick in, right? So despite large language models there, RT2 is out, but a lot of research has been carried on like this. So now if I look back, it's a little bit prehistorical. So back at that time, before, I think 2014 is about kind of dividing line. Before that, we were using simplified models, and we use some other multi-stage method in order to translate simplified model into a multi-degree freedom robot to do the dynamic working. And 2015, IIT, so we worked in Lorenzo and I worked in IIT before we have a fully developed humanoid robot. Everything is made in-house in IIT, in Italian Institute of Technology, joining forces between the ICAP facility together with advanced robotics department. So we built this here, so we're using a lot of optimization-based method. So from simplified model to optimization, and this is also optimization-based method, and some other imitation learning-based, this is also learning-based, and deep reinforcement learning-based method. And so it goes all the way down. So it was going from simplified model, completed model, and then shift from model-based to model-free, using deep reinforcement learning based on relatively smaller network, but not so huge yet. Okay, so this is how it looks like. If we use simplified models, we can do dynamic working pretty well. That's 2014, October, I think probably before October or around October. We made it work. So for dynamic working, it's not so complicated because you are not interacting with environments. So simplified model can work. But if you want to touch with different body parts and interact with the whole environment with elbow, with different body parts and roll around on the ground, if the robot needs to roll around on the ground, getting up and turning around, it's way more complicated to manually program how the robot should move using multimodal dynamics. So everything is learned using neural networks through reinforcement learning. At that time, this has been done, the fundamental work has been done during 2018 and 19. So at that time, it's very, very hard to squeeze different motor skills into one neural network, because now it's different. You can have prompt. You ask a big ChatGPT, right? It's a huge network. You can prompt it gives you a different answer. But for locomotion skill back then, we have relatively like 3 or 4 layers of neural network for motor control. It's very, very small, like an insect level. There's no way to squeeze them in, right? So the way to do that is to train different neural networks and try to kind of come up with a way to have a multi-expert architecture to synthesize them together using a centralized gating network to fuse them together in order to blend the different skills together. So nowadays, if you use ChatGPT, there are 8 experts behind it, and each expert is answering different things, and the output is something they cherry pick and fuse from different experts. So even the ChatGPT big models, because the brain gets too big, it's very hard to compute it. And in the end of the day, it uses kind of relatively smaller brain, like 8 different brains together, and do things in parallel, and they kind of fuse the best answer and output to you. Because the computer now is so fast, and the token is spit out so fast that you don't feel it from your back end, from your computer. I don't know why. Interestingly, I think OpenAI also picked up 8. At that time we did it, we also found 8. It's an empirical number, purely coincidental. I don't know why. Because 6 is a little bit not enough. 10 is a bit, they don't see the improvements. 12 is a little bit overkill. The performance doesn't get better, it gets worse. So when we get around, we get around 8. So it's an empirical number. But interestingly, several years later, I found out OpenAI also used 8. It's a magic number. But in the Chinese cultural context, 8 is a good number. It's an even number. It's a magic. So this is a little bit afterwards. We also carry on this. To be honest, this doesn't use foundational model. It just changes to graph neural network. So this just covers what has been published in 2025 last year. Just give a quick overview. I will just show you the capabilities. So instead of manually programming all the trajectories and to the task motion planning, what is happening here is that the neural network captures the structure of the environment. So we use graph neural network rather than end-to-end learning that learns everything in an implicit latent space. We use neural network, graph neural network to capture the structure of the environment, the representations, right? The nodes and edges. So given that kind of structure information, then we apply different reinforcement learning to learn how to move to coordinate multiple arms. So you can see that we can actually augment the number of arms into 8. So in reality, of course, we have 4, because it's very hard to mount this very heavy robot, the other 4 robots on the top. Right? It's very hard to do that. So in the research lab, we have only 4 of that in Mountain View in Google. So just for your information, so this is like can run in real time, and you don't need to manually design anymore. So it works in the car manufacturing. So I'll just let the video play here because I've skipped the background. So we have a patent of that. So Intrinsic actually is using this patent and work with car manufacturing companies. So that's real use cases, right? So you don't have to, because the work cell is so specific, usually it takes months for a human engineer to go there, test it, change the timing a bit, or collision happens, and then modify the via point, or using some small-scale optimization to change a bit. So it's a back-and-forth iteration, which is very, very time-consuming. But using learning, you can just put it in a computer. Usually, it doesn't take more than 24 hours. Just throw it in the TPU, the Google TPU, and that does the job, right? The silicon intelligence doing the job. So that's about one use case. The other is the collaboration for medical care, where we use autonomous driving technology in this case here. So for the lung surgery here, it's very, very tedious for human to go through all these kind of small channels. It's just like small channels or chambers you have to go through. And then you get a lot of mental fatigue by navigating through all these things. And in the end, you just want to remove some external foreign body from the human lung. And so what to do? It's like human driver. You have to go all the way down, and you're already getting tired. Like after half an hour, you can't find stuff. So what happens is that we found out actually for this particular task, it's much easier for AI to do the autonomous driving, right? So because you see the tunnel, it just goes there. But for human to remove the foreign body, there's all kinds of ways to do that. Of course, you can do it through VLE, which I will introduce later. But for the time being there, for the medical and surgical context, it's still it's not there, right? To remove the foreign body, that's too critical if something goes wrong. But navigation is still fine, because if it goes a little bit wrong, you can steer it back. So what happens here is that we use concept of shared autonomy as AI, like use the auto navigation AI copilot. So the human just needs to look. So it goes autonomously. Oh, you find the foreign body. Now I will think about how to remove this particular foreign body, right? Maybe I just, grasp it, or maybe I need to push it, or maybe I need to cut it and do something. So the physician just need to do it in the last step. So the rest of the time just watching. So it's just so much easier. So it's the work I've done. It's also published in the Science Robotics, basically. So I introduced 3 Science Robotics papers. There's still other papers I will skip for now. So this is best what we can do by 2023. The EU project for healthcare, it's about dexterous manipulation. You can see that the robot navigates to the target place, reorient the box, and open the box, and then take things out. So I'll let the video play a bit. Yeah, I will take this out. So the video is still a bit sped up. Okay, so this is what we can achieve by genius engineering with top researchers across UK and Europe to put navigation, path planning, task motion planning, and grasping. Also, of course, also visual recognition. So we engineer all these modules precisely together to do this one specific task. Okay, so this is not generalizable in this, or not scalable in the sense that whatever new task comes in, you have to hire this 10, 20, the top genius in the world to do this. And only those guys know how to tweak these parameters and how to adjust the environment, camera view angle, and so on. So that leads to, so once the project over, I was thinking like, how I can deploy this. But unfortunately, without new AI technologies and without the VLM or VLA capability, it's very, very hard to make sure the system will still operate well in a completely different environment, like in the real hospital, right, where everything changes. So we'll come to this bit later. So this is what it is like almost the best what can be achieved using the traditional methods. Traditional methods are not bad. It doesn't have the true intelligence behind it. Okay, it's just like if you count intelligence level like 7 or intelligence level like autonomous level like 7 1 to 7 is probably like somewhere half of the way. Okay, so this is just a little bit kind of background. And so looking forward, right? You guys are a young generation. You need to look forward. So the future is on your shoulders. And there are a lot of things you can work on. And today we can only cover more about the physical skill part. So other parts, like understanding the world, like VLM, embodied reasoning, and so on, that has been taken over and largely dominated by big tech companies, which we cannot, it's very hard for us to afford the fundamental research there. We can still use the APIs, but it's very hard to do research because the scale of people we are talking about here is about 1,000 people. So 1,000 researchers doing that, the VLM or water model, video generation, and they hire another 1,000 to do the labeling, annotation, and so on, or they outsource company like Skill AI somewhere in Africa or in India in order to do the labeling. This is the level of resources we cannot access. But to do the physical skill is something that we can still do now inside the research. Just a little bit to touch, this is not the final scheme, but it's just my view. One of the possible ways that can make things more scalable is to learn from a lot of things can be learned from the videos directly, and you can practice in your mental mind, like simulation, but you still need a little bit of practice. That's the real data. So you can have a lot of source of data. So it's like, if I don't know how to do that, do something, I look at a YouTube video, how to fix the mountain bike, if I have never seen mountain bike before. And maybe I will do the mental simulation because I can cheat as a human. I have word models, right? So that's my simulation. If you don't have that for robots, that's Isaac Lab simulation. So I simulate a bit of how I fix it. Maybe then I'll exclude it. Maybe I shouldn't do like this. I'll get my hands dirty, so I should use tools. So I simulate a bit and pick up things. And maybe I just go ahead and do it like zero shot, or maybe I will touch the tools and touch the parts and feel the friction and making sure that I can do it now. Maybe I will collect a little bit of real data, like if I'm the robot, I'm the biological robot anyway, right? So this is the source of data we can look at, and we can iterate our foundational model either for the robot or for us, as we're doing similar stuff. Then I think the more promising way is as a generative way that we can think about different kind of interactions like menu skills in a generative way. Like if I imagine like how to grasp it from top, I will imagine this posture. If I grasp the cup from here, I will imagine this. If I push it, I will push it like this or that. So I can imagine all these possible grasping poses before it actually happens. Then usually this kind of imagination happens in mind first, and then goes to reality with Dexterous manipulation, where when you really touch the object, you start to feel the tactile force, and you get a sense of touch, and then you know exactly how you should execute. So it goes down to the lower level of motor skills. Due to the time limit, so I wouldn't be able to put a lot of schematics. There's a long technical report there, but I can just leave the video play. If the sound doesn't get out, I can just explain you. Well, okay, this no sound doesn't come across. So I will just talk things through. Nowadays, I think there are a lot of robotic hands coming out. They become gradually affordable for institutions, not for individuals yet, about 7,000 pounds, 8,000 pounds each. Yeah, by the way, I bought one just for experiments. If you want, you can try it. But it's not, I think really institutional levels is about that. So this is the, I think this is 21 degree freedom. This is 12 degree freedom. So usually it's between 12, 16, or 20 something. So the challenge is that if it doesn't use tactile sensing, and it's very, very hard to pick up an egg and soft objects like that. And the problem we try to solve is that we find out in physics simulation, the contact is not so realistic. So when we knock this, and then, we have the soft material like here, and it's very, very hard to simulate softer materials. And we tried it many, many times in physics simulation. If we only look at the rigid contact and get the force reading from physics simulation, it is so untrue. So we try to put a lot of rigid bodies, like red dots, like cubes, as a new joint or rigid body. Touching simulation, we put all the dots over the hands and touch the objects. we found it doesn't work because the physical context is so different. So you know how the forces look like in simulation? We went, well, one body contacts another, it like jumps like that, or jumps like that. But in the real reality, if you touch it, it goes like this. Right, so the response time, the feature, the temporal changes, or the temporal dynamics is completely different. And also weirdly, we find out that even in simulation, we did a grasping with parallel jaw gripper. We just squeeze it like this, and we get this reading and this reading. They should cancel out, right? But actually it's not. Then they don't have the exactly same magnitude. Like, what is happening? Like, what is going on in the Isaac lab? So like the other is like 20% off. I don't know why. And the force is very, very strange. It goes up like this. Once we get a reading like this, and it jumps out like this and jumps back and stays flat. It's completely unrealistic. So we found out to encode like that, when we translate that simulation results, train the robot there in that simulation, where the physics is so different from the reality, we deploy it doesn't work. So the way to make it work is it's cheating a bit because the spatial motion is still quite accurate. The force reading getting from the APIs is not accurate. The spatial relationship is still there. And despite still rigid body simulation, there's still kind of certain level of penetration between objects happening, dominated by wrong, not entirely right physics. But somehow, if we get spatial readings out, compute a distance, and assume it's spring damper system that gets compressed with that distance, and we get that kind of pseudo imaginary forces, it's kind of right. So that, and because the real hand also has the tactile sensor like tactile pixel, which is small kind of balls of magnets hidden there in the rubber. So when this rubber gets squeezed, all these point of magnets gets, they are moving in the space. So if you put Hall sensor on the bottom, you do the triangulation like GPS, and then compute where, and then they recalculate what is the forces applied at that dot. So we find out if we simulate it in the same way like how the magnetic Hall sensor-based tactile sensing work, it's kind of right in the sense that you get all these kind of contact points. It's probably not so clear, but just, all these kind of blue points are the contact points. We treat all these contact points like cloud, and we between the simulation and the real world, all these kind of contact points like clouds, they're not exactly the same, but the pattern is very, very close, very similar. So what we find out that actually it is easier if we put all this kind of sensing, the complete sensing into the robot and do the learning. So we can control the forces. So normally people just learn the grasping and don't control forces, but it's very, very hard to use it in reality because you want to grasp hard object, light object, heavy objects. So we find out we can actually control it. So this part is just show it's adaptive. So the reinforcement learning grasps any kind of object in the simulation. So it's very, very adaptive. It's adapted to different forms and so on. If I come back to the previous one, so you can control the forces. At 10% or 100%, I just squeeze it. Right? So I just squeeze it if I increase more percent. So I have a controllable input to the neural network that increase from like the base level like 10% up to 100%. 0% is not doable because you need to overcome the friction of the motor and so on. Okay, so the last bit is most interesting, is that, so we did the in-hand rotation, and I think so far no one has done this without with continued rotation, like without any feedback, without any direct orientation feedback. It's purely guess like blind from this kind of sensing. It's around 1 minute continuous rotation. So if we cheat with internal sensing, it can, like we put an RMU sensor inside just to cheat to see how it works. It can rotate and tune as long as 5 minutes. So if you just do the blind like this, it's like 1 minute. It's pretty good. So you can see it's very, very robust. It will touch it. It doesn't touch it, it'll go back. You see? So we just let it go. So it touches and then it rotates. So if it doesn't touch it, it will go back. Okay, the miss out. So all right, we are pretty bad in the sense that we just tease it, or just press it, just hold it and doesn't let it go. And then we're trying to touch it with the tactile sensing in order to reorient that cube. Yeah, so this is the force controllable, so you have seen that. And this is with external sensing, because the neural network needs this input, the state of this cube. So for the vision, we haven't done the end-to-end, so in this way we just printed a different QR code on the surface and let it see the orientation. So if it doesn't touch it, it goes back, trying again. And one reason it can't do it is that because the finger, the thumb, has 1 degree freedom less than humans. So it can only have quite fixed trajectory. It's not that flexible, right? It cannot rotate in this direction. So that's why it can't reach out so well. But still, it works pretty well. So this is about sim to real. So you train things in Isaac Lab, which is free. You just need a good laptop or a very good desktop. NVIDIA is developing all this Cosmos, Omniverse, and all these simulation tools. You can do that in the simulation, develop your own AI, algorithms, and deploy it in the on the hardware. So this is about sim to real reinforcement learning. Still no intelligence, no kind of brain level intelligence, and so on. This is robustness test. We have seen this. I will skip it for now. Is there any questions before I move to desk scale, which Lorenzo and I have done before? Any questions?
Yeah, I didn't quite get the hard sensor part. Could you just go back there?
The hardware.
Yeah, the hardware setup, like how it's set up, how it physically detects contact force.
You mean the tactile, right?
Yeah.
Yeah, I think there's no particular schematics here for the paper presentation. The product of that kind of hand or the tactile sensor will have much better schematics. So I think probably I can use this as kind of prop. So let's imagine this is the magnet. So do you know Hall effect sensor? Hall effect sensor, so basically can detect, for example, the distance of the magnet. So there's 3 of us here. So if the magnet is here, right? So imagine we inject the jello around it, so it's kind of moving. If I press, it's moving. So I can detect distance. So if I press it down, okay, we know what the XYZ changes, and we know where it is. So given the stiffness of this jello or the rubber, and we can actually calibrate how much force it is for this. So if that is more stiff, with the same force, it moves a bit. So if I want to have better resolution, I put a soft silicone here. So with the same force, it will have large displacement. Maybe it's not linear, but it will be calibrated before, from the factory setting. You can know those numbers. So it's similar to the GPS, right? There's 3 GPS, and you can do the triangulation. You calculate where it is. Yeah. So this is how it works regarding the tactile sensor.
So the magnet is measuring the distance of the magnet moving.
Yeah, that's a good question. So
fixed inside the finger.
So let me clarify. The magnet actually is a passive element. The magnet is just magnet. That's the beauty of this sensor. So the Hall effect sensor is active with electronic. We have a PCB board. We have a Hall effect sensor, 3 of us, and the magnet is just passive. So the magnet is moving, but we can detect where it is. So that's a good thing about it, right? So maybe I think in the next design, it will be removable in the sense that when the rubber gets old, you can remove this. We are the same, and they put a new rubber. I think in the future they will design it. Yeah, I think if you're interested in the tactile sensing, Lorenzo is the best person to ask because, he's doing that. Yeah. So the next thing I want to discuss about is I want to share with you the desk skills. I'm not sure how much Lorenzo has talked about this with you. Let me see if I can bring over the. Yeah, I think. Yeah. So I will only cover the rough idea of it. So we have done this before the VLA paradigm came out. So at that time we were thinking that if we look down, if we look at the human grasping synergies, right? So the hands object interaction can be categorized with 33 types. If you look at a normal daily interactions, they are finite number. It's not infinite number of atomic skills. So that's the rationale behind it. We have reaching, touching, flip, and wipe, all these kind of basic atomic skills or very small sub-skills. So if we look at the long sequence of manipulation tasks, usually it's a combination of them, just a different order or sequence, right? So the rationale is that if we can learn each of them, through imitation learning, and then when we look at a new task, we don't have to learn from scratch. We might as well just recombining the learned imitation learning-based sub-skills into a new sequence. So that's the rationale behind it. So how the imitation learning is done is that Lorenzo has invented this very good interface that allows the operator to map the motion, the wrist motion and hand motion to the arm motion here. So in this way, with the collection of a handful of real data through this kind of teleoperation-based demonstration, the robot is able to learn a particular type of skill. Right then, on top of that, you can learn, for example, a library of different skills. Then by combining them, you can compose whatever arbitrary long sequential manipulation tasks. So that's the basic idea behind it. And I will keep the video playing just for a short while. And of course, if you want to know more technical details, Lorenzo is the best person to ask. No. Right. Do you have anything to add here?
But maybe we can add later, yes.
Yeah. Okay. So let me go back. So this is about what has been done in terms of kind of challenging long sequential tasks that you can do before the VOA panel. So this is something that we can manage in the lab scale much more easily without requiring massive number of people, right? So one student can do.
Sir, in this course, did you combine the skills?
Sorry?
You combined the skills of this course, right? You didn't just learn, right?
So you learn each individual atomic skills, and then when you look at the new skill, so this is something I didn't mention, but it's explained in detail in the paper that we also learn kind of pattern recognition from the features such as like the kinematic of the finger distance of fingertip and all this kind of feature. So through that, actually, when it comes to a new sequence of tasks, you can actually recognize which sequence is which kind of task. So first you identify this is kind of grasping, this is pushing. And then similarly by looking at a new sequence task, you can recognize which section is what. And then you can invoke the sub-skills to do that. This is like what we have done before the VOA paradigm, but this is kind of more like a grammar, a syntax of manipulation where you can compose different words. Right? So it's a recombinatory in this way, and the size of the neural network is not massive. Yeah, that's a very good question. Yes.
Okay, I'm just curious, how did you generate the sequence of the sub-skills that you need to combine, and how did you specify the skills as well? Is there some kind of encoding or embedding for the skills?
Yeah, this embedding of the skills, as I explained before. So we have iterated several different versions. And this is a very good question. I think actually we can expand. Actually, we can even take one step further in the sense that for this work, we try different ways of embedding, and we find out sometimes, I think in the beginning we simply encode all the cues. It seems doesn't work. So we have to consider also kind of the interfinger distance and so on in order to distinguish one from another. So there's a lot of kind of human-driven design behind it, right? So it's quite different from the VOA other kind of large foundational model base. So you no longer annotate in this level. We do not invent how to encode it. You throw enough data, it will just learn it. Yeah. So we indeed need to do this encoding in order to encode each different type, and also use the encoding to recognize different different type of skill from a long sequence in order to compose them again.
Okay, and the task is also embedding. The task is specified by embedding, right?
What do you mean?
So you have a new task that you'd like to carry out. Right?
Yeah.
So how do you represent that task to ask the model to generate the sequence of skills?
Okay. So this kind of detail, to be honest, I cannot recall very, very clearly, but definitely if we dive into the paper. So in the end, when we demonstrated, we use a new sequence, and then we compose this and to do it. And we can look at the paper for more details.
Yeah.
Do you remember?
So, I mean, maybe
Yeah.
a separate answer, I'm not sure if. So after we teach the individual skills, then when we want to tell the robot, okay, now do this sequence, we first teleoperate once the sequence.
Oh, okay.
So we tell the robot by the teleoperation
Only once.
do this sequence, right? So, but that we do it only once. So the long sequence, we don't need the robot to learn it.
So you
We just use the teleoperation to tell it to the robot. Like,
you
okay.
demonstrate the skill, a composition of skills, and then you decompose it into the sub-skills, and then you
Yes. So,
Yeah.
so when we do the demonstration of the long horizon sequence,
Yeah.
the robot uses that representation to decompose in skills, and it kind of understands, okay, there is a grasp, there is a lift,
Yeah.
there is, and then because it decomposes in the sub skills, then it can execute.
Yeah.
Right, and you did the decomposition with like some kind of sequence model, right?
So I think this bit is what I couldn't recall just now because you demonstrated once. So from all this kind of sequence of kinematic or the data, from the encoding we talked about just now, it can recognize which section is which. So basically, it's kind of pattern recognition.
Yeah, and then we just execute them.
Yeah, then you execute. The advantage is that it doesn't use the large foundational model, doesn't require massive data. But the disadvantage is that if the demonstrated one has some parts falling out of the library, so your library had 10, you execute something beyond that, then if you use same encoding, it will still tell you some probability, but actually it's falling out. The neural network still spit out something out of the 10, but actually you are demonstrating something else. So of course that's the limitation of it compared to the foundational model approach. But this is more like lightweight. Yeah. So it's a combinatorial within the skill set. Yeah.
What year was it?
We were doing this in. We started it before the VLA stuff. Of course, the research carried on for more than a year, iterated. Then you have to go to the review, and the paper gets published much later. So the seeding idea happened before the VLA stuff. So the next, I want to talk about what I've done to the industry. Now I'm back, but I was in the industry for about a year or so. So we did this kind of shared autonomy for end-to-end learning, and we found out from all this video you have seen, we're using Grapper. It's relatively easy, 6-degree freedom plus 1 open and close 0, 1. But if you want to wear an exoskeleton like this, like the sci-fi movie, very, very crazy exoskeleton, you try to grasp like the bottle, and then you don't know, it drops again, then you lift it again, it drops again, and then you try like 1 hour, maybe you only get a very nice demonstration of 10 or so. We found it's a very inefficient way of collecting data. So in the end of the day, what did we find out? We used 2 different VLAs. Rather than do it everything like very ambitiously at one go, we first trained the VLA that uses the tactile sensor for the hand only. So we call it desk grasp VLA. So a hand, just a hand. So I called it like a little monkey, right? So little monkey, is this just the little monkey with eyes and all the limbs? So it knows what to grasp. So I trained the little monkey first. So the monkey, once the monkey sees things in the range, they will just grasp it in all kinds of different ways. So we call it desk grasp VLA. So it's trained using human data plus force-sensitive LSTM, this kind of self-adaptive data. So the self-adaptive LSTM is blind. It doesn't have eyes. It's just blind. But it knows how to use the tactile information to do it. but it's limited. It's not so diverse compared to human hands. But the human don't have the tactile sensing, right? But we are very, very diverse in terms of how to grasp it. So if I train only one of them, it's not very good. It's not very, they overfit. So what I do is I mix all the two different data sets, right? The human one is not perfect. It doesn't control the force very well, but it has very diverse posture, hand posture, which is good. And this one knows how to control the force very well. And I put those data sets together and train the hand VOA only. And then the hand knows how to grasp things very well by itself. I call it autopilot, AI copilot. So I don't have to worry about how the hand is dealing with it. So when I'm telling the students, I'm having the fish rod and I have the little monkey on my fish rod, I don't have to care about it. So when I do teleoperation, I just put the little monkey there, the monkey will do the job by itself. So it's just a joke. So the student is very, very, that just removes all the cognitive load. So previously, there's nobody who can operate more than half an hour. Usually 20, 25 minutes is the limit. After half an hour, I think there's no single person who can wear a exoskeleton doing this for half an hour. It's very, very cognitively draining. But with this, you can easily collect it because you don't need to think about it. You press the button. You just go there, A, B, press the button. Because the VOA, the hand level, is doing all the job. Don't have to think about it. I just move there. Okay, that's the right posture. But for AI, it's very, very hard from the beginning how to approach the object in all possible ways. But we are good at this. We just have the open hand, and we just approach it in all good ways. So we don't need to think too much with the handle. We just do it. And press the button, activate hand VOA, the VOA does the job. And almost more than 95% of the time, it doesn't slip. So it does the job very well. So I almost get all the good data. So the bad data case is very, very low. It's very, very uncommon that I get bad data. So almost every pick is a good pick. So that gives a very beautiful story that the student is happy to do it, right? So student is not like those movies, the YouTube video you have seen, the Elon Musk's factory, whatever, so many people are doing this. And there's no PhD student, no research student who want to do that. So that's why we invent this and make students' life, researchers' life, very, very easy because they're happy to do it. Sometimes, if you want to inject a new data set, you don't need 100. Probably something like 50, something like additional data set you added on this, that's enough. That takes you only 20 minutes. So sometimes when we collect data, I was having dinner, I would say, or having a meal, I would say, can you wait for me? I want to collect data by myself. I want to do it in this way. By the time I finished my meal, I went help the student. I finished it. It's very quick, 20 minutes to get all the data I need. And they put it back to training for 4 hours, you get it done. So basically, we make this data collection very easy. We can get a high quality, stable grasp data in a very short time, and then put all this data together for training. This is the typical training scheme, if you're familiar with this. And we found out if we deploy it just like this, we collect all the good grasps, train the VOA at once, deploy it. Usually we get 80%. But it's very, very hard to cross 90, 80, 85. But it's maybe sometimes you get a one shot like 90, 91. I've done this recently. But it's very, usually you are falling between 80 and 90. So here is what the collective teleoperating data flywheel kicks in the sense that the trick, what is the trick? The trick is that I train like one version of the brain and then let the brain do the grasping by itself. So when it's doing right, that's a good data. So I have data set original one, I teleoperate it. The second data set is what it does by itself. It's also a good one, but it's different from my demonstration, right? Because it's doing by itself. And the third one is that when it's almost getting there, but usually it's doing something like this. So just miss a tiny bit and push the ball over. So what I do is it's like optical mouse. So we have the incremental intervention in the sense, it's just like a mouse, and then now I kick in, I just bring it back. Now then it grasps it, and then I let it go. So I do not handhold the child all the time. So when the child is doing something, I just push it. Okay, that's the way, and then the child is doing the rest by itself. So that's kind of corrective data. I also collect it in, and it's not massive, right? So it's not like the total takeover. So you only correct when it's necessary. So you have this complementary data. So what happens is that We have human demonstration data, and we have the child is doing something by itself. It's different data as well. And how I handhold and help the child. So put these three together and put it back to the foundation model and fine-tune again, then usually it boosts to 90% more just by one iteration. So if you keep this iteration going on, and they will gradually go to 95. But so far it's still manual. It's still manual it's still human in the loop, right? So, but the beauty is that we can prove that the data engine, the data flywheel is useful to improve the performance. Okay, so here's the video. So the teleoperation. Let me see. So I'll just let the video play. So we have, so the human only needs to do this, the risk level. So the sound doesn't come out. I will just do the talking. So basically just showing the different training steps. Like this is the one shot you train, and this is kind of closed loop, right? So this is like, I get all these things done. I go to the exam. I make some mistake. I come back and what kind of mistake I made, I just correct it. And I go to the exam again. I will do much better. Right? This is showing. So I cover the camera here, but once it can see the tactile, then if I blindfold myself, it's fine, right? So if I need to grasp it, I need to see. But once I grasp it, I close my eyes. I can still hold that in my hand. So that actually is very, very useful technique that allows me to collect good data right away. So you can see there's almost no bad data. I can just pick any object. So I can collect it like almost 100, like 99 out of 100 times, I just get it right, good picks. Right, so I don't have to wear this skeleton and try to figure out how to grasp that tiny bit stuff. And here it shows that how it collects data, just like it's very quick, just A B, you just grasp it. And later there's an intervention. For some of this kind of, I will just skip it. So you can see the collection. If it drops it, it will just go back. Oh, it's a bit too quick. There's a video later on. I will also show you. So you can see if I block one camera, it's still fine. So it's still quite robust. So we have some tiny tricks which you can read the paper. I wouldn't expand those kind of details, but there's some tricks you can enhance in terms of feature extraction. Yeah. So this is the intervention. So sometimes it just misses a bit. And you now you intervene, and then you release the button. It's still good data. You don't spend too much time, right? You see it kind of missed the point. You just bring it back, and you let it go. So this is just becomes much more efficient. Okay. Yeah. So basically, there's some just this just schematic just shows that how you map from human this kind of incremental move, just like a mouse. So you start to put your mouse down, move it, and you lift the mouse up, something like this. So it becomes very, very flexible for the data for the intervention. So this is just to show that the same method is also useful for different hand. So you can also pick up quite small stuff, right? Almost no failure, very, very low failure rate. So later I also pour a box of objects to show that it's not staged, right? A lot of times people just stage things in scattered objects, put scattered objects on the table. So I just pour the whole box of stuff there. So the hand VOA is very, very useful. Okay, there are more, so I probably will skip it. There's a very, very long video. It's not successful anyway. So this is something that we cannot pre-program. You can't use control laws, principles, rule-based system to do it. And whether or not we can use the previous grasping stuff, I'm not so sure. I haven't tried it. There are just too many different objects there. It's just too hard for us to just do the imitation learning one by one. Yeah, it can do all the job. I guarantee you. There's a video playing till the end. I will skip it for now. It's just too tedious. Okay, all right. And just to show for tissue paper, it can also work. It's also very long. I will just jump to the end. It just finished all the paper. It's just the whole tissue box. The whole tissue paper is gone. Yeah. So the previous one, we have shown that like how we can do the learning in the smaller scale and recombine the autonomous skills using smaller models, and we use VOA as large models. But they also require a lot of collection through the hardware. And this work we talk about learning from videos. We started this idea actually in 2024. Let me pause it. In 2024. And I think last year, I clearly remember it's May, around May, Tesla is saying that we are also doing this. But there's only news. You don't know how to do it. So I think nowadays, at the moment, I can say that I think there are two ways of doing it about learning from videos. One is to learning from 2D. The second is learning from 3D, which is harder. So what we do here is learning from 3D. Okay. So briefly speaking, we reconstruct 3D scenes from the 2D image, and then we learn in ISAC when we deploy it. So learning in ISAC and deployed is very similar to what we said before about the hand. We do things in simulation and deploy in reality. We close the sim to real gap. But extracting 2D 3D information from 2D images or videos is really, really hard. So there are a lot of small tricks we need to do in terms of getting the information of object and information of a hand. So if we directly take the trajectory, it's not going to work. If we directly take a human trajectory, it's not going to work. We need to still inject a little bit of uncertainty and let the policy learn by itself. So it's robust enough to counterbalance the differences. So this is synchronized assembly. So just you can see we randomize different object position. So you cannot always train it on a fixed position. Then it doesn't know how to handle the uncertainties. So you need to randomize it in the simulation, which is easy. So here you can see that this original video reconstruct the 3D information here. We extract 3D information. We put that 3D information in the simulation. And also in simulation, we randomize the different scenarios around the nominal ones. So the robot can learn the assembly. So it's a synchronized way. The previous one synchronized, this is asynchronized. So it's different sequential movements. So you can see the original video, processed one, and the simulation. Right, so you can see that simulation works, and then the last bit is sim to real, which is really hard. Unfortunately, we only had 1 week to do 1 week before the deadline. So there's still some hardware issues that, from step to step is not very continuous, but it's some hardware engineering issues. It's not the issue in principle. We only had 1 week to do all the experiment before the ICRA deadline. You can see not so bad. So you have seen the promising light, right? So I'm pretty sure as long as the proof of concept 021 is done, to improve it, just a question of time. So that is very high-level principle. Just the data processing pipeline is quite straightforward. As you can see, you get 2D, and you try to extract all the information of the hand and object separately. There's some techniques, tricks, how you can map the hand. It's not easy. And then, of course, there's some occlusion stuff. So we did a lot of kind of algorithm tricks in order to get hand motion correctly, especially the finger position behind the objects. So you can see it's kind of imagining the back side of the moon. So once you get this done, then you do all this learning, as we explained before. So, okay, this is the same video, just without cropping. Just there's some engineering issue regarding hardware. It's not torque control robot, it's position control, so it's a little bit not so smooth and sensitive to some little bit discontinuity. So at least it works, which is good news. So here's just something else that we have improved later on. You may not see the differences, but I can explain. You can see this the continuous movements of hand. So this hand, so that is my hand, as you can see, but this is actually not my hand. It's a model of generic human hand fitted into my shape. So it can fit into your shape and your shape and as well. So this is optimized, the generic human hand fitted. And the beauty of this, a tiny trick of this, that I can do all this point touch, and also I can do it continuously. You can see I can slide between 4 fingers. So we did a lot of optimization tricks that we do not. So usually people judge what is the distance, and they think, oh, I'm touching this, I'm touching this, touching this. They use some threshold to say, you will see the finger will jump from this to this, right? So 0.5, 0.5, which one? Like 4.49, 0.49, 0.51, then it starts to jump. But we solve the problem doing some tricks and by continuous optimization, so you can do the sliding motion. So this is about learning from video. This is pretty much the introduction of all these things. And here is something else I want to talk about in the beginning of my outline regarding human level dexterity. So this is not a complete research outcome, but rather just the beginning of the new research that we can possibly do. So the previous algorithm I've shown you there are a lot of things that have been patented. And this one has not been patented yet because we modify on top of that regarding the glove, because all the previous methods are purely based on vision. The glove is something different. The glove gives you direct measurement, and there are some other ways to do retargeting. You can see, you can do this. So you can put, so basically they can pinch grasp your credit card and pull it out like this. Right, so you can do like this, and then can also do the sliding between different fingers. So you can put the poker card and slide, a stack of poker card and just slide it out. So you can do this kind of continuous movement, and also maybe count how many dollars, right, in like this. Yeah. So basically, we did this, and then I returned back. So I'm quite interested if we can get a Manos glove. The latest one is $9,000 US, and we can do something better, because this is the old previous generation with one magnet at the fingertip. The new Manos glove has one more somewhere here, so it has 2 direct measurements, and that drastically increase the accuracy of the finger motion, and we can definitely do more. So what to imagine? What does it mean if we have a glove? I can unscrew the cap. And the interesting thing is that look at what the hardware can do. Right. So the fingertip, the thumb is quite big, so it's difficult to pick up, but still, it is possible. Just pay attention. Just one more second and see what's going to happen. Right. If I try to close it, and students say it's tight enough, right? So the water doesn't leak. So I can screw it and unscrew it. They're good enough. It's tight enough. The water doesn't leak, so it works, right? So the robot's hardware is about getting there to serve you a cup of tea, something like that. So this just to show you the capability that what you imagine. So that will cover a lot of interesting recent research progress in terms of manipulation. In the end, I would like to touch a little bit about locomotion, because when I was doing my PhD at that time, a lot of robot hardware is not quite there yet, so it's very, very hard to do manipulation research. And locomotion was not easy neither, but it's relatively easier. Still, I have students in the group who are doing this. Milo is just down there doing some experiments today. So due to time, I will skip a little bit details, but just in the high level, I want to say this is a generative approach. This is a different approach from what you have seen, like those kind of kicking, dancing robots. So those kind of robots you have seen, like back flipping, kicking, dancing, it's using the deep mimic or modified method from deep mimic, meaning that they have the whole body motion trajectory recorded, and then they apply the neural network learning to modify around it, adding delta joint angles. So you have the motion trajectory like this. So it's like you already defined the highway, right? The trajectory is like the highway. That's a highway. And they say this is the width of the road, and you can drive around the road, but cannot drive out of the road, right? So that's why when all these robots during the demo show, when those robots fell down on the ground, they start to do all these movements because, it can only modify around that nominal. But this is different. It's the motion is completely generated from new every time. At every control loop, it generates a whole sequence of motions, and purely from text. So you go forward, and the robot will generate whole body motion to go forward, go backward, turn. So you only need to tell with very, very high-level command, and the distribution policy will generate a whole sequence of actions. So just let you see how it works. We solved the problem. We spent more than 3 months to solve the problem. The limitation is that the original method needs a very clear data about the spatial velocity of the robot, but we don't have very good SLAM system or absolute velocity estimate of the robot. So we get diffusion method to learn implicitly in its latent space what is the body velocity. We don't directly get a measurement, but rather we just measure all the body states and try to learn from the latent space. And in that way, we avoid getting this input, and then the policy become more robust. So we can just work around it when we give this with the command and then start to generate whole body motion. Experiments are not easy in the sense that we only have one robot, Unity robot downstairs on the ground floor. So the method is that we use a very good teacher policy that has all the complete observation of possible states and learn all the motions. And we use the teacher policy in simulation to generate a lot of data. By adding noises, we generate a lot of data. And then using that generated data, we learn different kind of whole body distribution-based policies. So this is velocity control that to show that we in fact give a commanded velocity, not measured one, a commanded velocity, so that the robot learns how to walk around. So you can see that it can also do all these kind of movements like you have seen online, like all these whole body movements, kung fu fighting and all the things. Yeah, really looking for, if we can afford 10 different robots without worrying about breaking them down, we can possibly get all the things done probably within 1 month's time if you guys are also engaged in the research. But unfortunately, we only have one robot. We should be really, really careful. You can see the kung fu fighting can be done in simulation with no problem. Yeah, it's quite scary because I don't think I can hold a one punch because it's all metal, right? Okay, so this is what we can do in the lab. At the moment, we are still, because of safety and the fact of having only one robot, we can only do human-like walking. It's not so bad. So you have seen a lot of human-like walking on the internet from Figure Tesla and a lot of Chinese companies. They are very, very impressive, and we thought they're probably quite hard to do. And it turns out actually, in fact, one UCLPT student can do it as well. One UCLPT student plus another student who can help, and plus 2 supervisors. With a small group, we can do this as well. Just, at a smaller scale in terms of 0 to 1, it's not a problem, right? It's really about, whether or not you can afford. Like those companies are making hundreds of robots, like Chinese company making hundreds of robots in their warehouse. So if they break one, they take another one, right? They have usually 100 to 200 people working there. They have done that job, amazing job. But think about it, the manpower we have, and it's already great that we can have a human-like walking. It's quite elegant walking downstairs. Okay, so with that said, I will conclude today's talk that this is the grand vision we want to do, not just in terms of brain, but also in terms of the physical capabilities. That's we bring the intelligence from the world of bits to the world of atoms, which is the physical world. And 2 years ago, we were thinking about doing the motor cortex and doing the task planning separately. We can still do it separately nowadays, no problem. But the interesting thing is that as time goes by, we can see more and more different new paradigm coming out. Even now, I think the VLA has been challenged because the VLA is built on top of the VLM backbone. The VLM is looking at the text to image or image to text, the question answer stuff. So it's looking at the objective of training VLM is to look at the image and tell what's in the image. So it's a static image and a text description. But what is missing there is that when it comes to the physical world, if I want to push this chair, all know the chair will, broadly speaking, moving in that direction if I push it, but not the other direction. So it's not only about static images, but also about temporal grounding to the real physics. And this training is not there a priori by design objective, right? When you designed it, it's not there. So when you take this backbone and train the VLA, meaning that you have to collect a lot of human teleoperated data, you use a lot of humans, right, to teleoperate robots to collect a lot of this kind of data, and then use data to retrain the backbone. Because the backbone doesn't have that, right? Take a look at the image. What is this? This is a room, bounding box. What is that? That's a street. That's the coffee. Right? It doesn't have the physical grounding. So training this is much tedious because you have to collect so much data to bring the temporal physics dynamics on how the physics will unfold in future. You'll bring this knowledge into this and train it again. Of course, it's going to consume a lot of data. But what if you have word models? A simple word model is kind of video generation, like Veo, like from Google. So cut a tomato. So it generates video of cutting the tomato, which is pretty good. Right? The tomato is quite consistent. Picking an apple is quite consistent. So meaning that the video generation backbone somehow learns the underlying physics in its latent space. It knows over the time horizon what is the temporal dynamics and temporal changes that will happen in pixel level from frame to frame. So meaning that it has captured physics in some level. So if you look at those latent features, you grab the latent feature, you use this latent feature to tell or inform how the action should behave in order to interact with physics. It will be much easier because the information is there. You don't have to train from scratch. So meaning that what is coming out in the past few months is that the word model is rising up based on video generation. And you see just from 1X CEO's speech, it's just coming out. And I also saw a paper like back in October from a completely no-name lab that has done it. And it's very, very disruptive technology. So this is really changing fast. And I have great hope that you guys can really spend your energy and look at all this new paradigm here. It's data-driven. So we have gone through all these trajectories. So I've gone through this wave, right? Optimization wave, deep learning, and learning-based control, and now foundational model. So I'm riding this wave here, but I cannot ride too long till the end of this. And you guys need to carry on this mission to push science further for the good, right? So the future of coding, as I spoke with some very, very top-level tech people back in the beginning of 2024, we think this is how future programming will look like for robotics. You simply will just tell it by text command, and it will have all these building models, tactile, vision, audio, probably smell in the future. And internally in the brain, it will just call all these modules and make some decision, reason, and just start to do it for you. So now you are doing, okay, I have my homework doing this. I copy this. Look at the picture of the schematics. Look at the question I copy paste. Can you come up with a solution how I can get a homework done? And then the ChatGPT or Gemini will tell you all these things, right? In the future, like, this is my room. Can you walk down the room, prepare coffee for me? And you can find my new coffee I bought from M&S in that cabinet. And you program it, and then your robot will just do all the things like what you do with the GPT nowadays. So that the future coding of robotics will be something like that. So with that, I will conclude today's seminar talk. Thank you so much.